Uh, Good evening, all. It's a pleasure to have Professor Nishal Verma from IIT Kanpur today. So now I request student to introduce Professor Nishal to the participants.
Yes, ma'am. Good evening, everyone, and welcome to our Advanced Computational Intelligence Techniques for Engineering and Science Applications Faculty Development Program. We are honored to have Dr. Nishil K. Verma, Professor in the Department of Electrical Engineering and IIT Kanpur with us today as a guest speaker. Dr. Verma is an expert in the field of artificial intelligence and has made several significant contributions to the research and development in his area. His research expertise is in AI-related theories and its practical applications to interdisciplinary domains such as machine learning, deep learning, computer vision, prognosis and health management, bioinformatics, cyber physical system, complex and highly nonlinear system modeling, clustering, and classifications. He has published more than 250 research papers and 4 books in the field of AI. He is also serving as an associate editor board member of various reputed journals and conferences, which include IEEE Transactions on Artificial Intelligence, IEEE Transactions on Neural Networks and Learning Systems, and many more. He is a awardee of Devendra Shukla Young Faculty Research Fellowship by IIT Kanpur for the year 2013 and 16. He has also developed several AI-related key technologies for the Boeing Company USA and organized AI-related workshops, conferences, seminars, and short-term courses, etc. The complete session is divided into 3 parts, from 7 to 7:50, the lecture, then a 10-minute break, followed by another 1 hour lecture, which will be followed by a half-an-hour Q&A session. I'm sure you will find Dr. Verma's insights and perspective to be both informative and inspiring. We look forward to a lively and engaging discussion. Now I request Dr. Verma to kindly begin today's session.
Thank you very much for a nice introduction. Thank you, Professor Meenakshi Tripathi, for inviting me to this faculty development program.
Thank
And
you, sir.
thanks
Thank you for accepting
to
the invitation.
okay. Thank you all the participants, and I welcome to my lecture on deep learning and deep fuzzy networks. So let me begin with the introduction to deep learning. And before deep learning, yes, we should at least familiarize ourselves briefly to the normal learning, right? That is also called sometimes shallow learning, right? So let me tell you that in AI, in artificial intelligence, in deep learning, in machine learning, there is a word which we cannot avoid is learning. So let us understand this term first and why it is really important in AI, machine learning, deep learning. So why learning, right? Learning basically is correlated with intelligence, and we know that right from the childhood we gain intelligence by refining our learning skills. Okay, and these two are interrelated. So better is the learning, better is the intelligence, right? So in the AI, basically, normally what we do, we we facilitate the intelligence through artificial learning. So when we talk of AI basically refers to the non-living beings or non-living being models, or the man-made stuff, man-made machines, where we are embedding intelligence by using suitable learning skills or the algorithm which facilitate learning, right? And these models are nothing but termed as machine robots and like that. So let me begin with the major landmark where we get a clue of learning, and you see, it was the time when McCulloch and Pitts joined hands together to develop a mathematical model of a neuron. The question comes, why the neuron? Right? What was the motivation of developing the model of biological neuron, right? So basically, we all know, and that time also it was realized by the researchers that, you see, our intelligence, the natural intelligence, that is because of the gray matters present in the brain. Okay, and we all know that no less than hundreds of billions of neurons are there in that gray matter, which God has gifted us, and it is natural. Right? So these are natural neurons, and for carrying out certain tasks, for carrying out certain processes, no less than hundreds of thousands of neurons, together act and perform that task. All right. So they form the network, they join hands together, and then they basically, perform that task of learning, and accordingly, the the decision making, or that task, whatever is the objectives that are fulfilled. So it was realized that time that it is the neuron which is the main constituent or the facilitator of the intelligence, and which basically provides the field of learning, where the learning can happen through the experience, and this experience actually is provided in terms of the biological signals to the inputs of the neuron, right? Like from the dendrites as the input nodes, and the outputs are coming through the axon, and further all the axon buds are connected to the interconnected inputs of the neurons, successive neurons. So that time McCulloch and Pitts, one was the biologist and other was the mathematician. They both came together, and they basically developed a mathematical model of a single neuron, which you can see here. This is the natural neuron. This is the natural neuron, single neuron, right? So you can see here, these are the dendrites. The dendrites through which the input signal goes into the this cell body. This is cell body, right? You can see here the cell body. Okay. So in cell body, we have a nucleus, and we have a fluid basically, right? And every neuron has different characteristic of this fluid, and which refers to the activation function here in the artificial neuron, or the mathematical model of the neuron. So here the inputs are taken by the neuron through dendrites, and these are processed as per the characteristic of the cell body fluid, and then impulse signal is generated on the axon, and these axon basically have some discrete signals available, and these discrete voltage signals basically are available to all the axon terminals, and which the successive interconnected neurons can take through their dendrites, right? and the connection in between the axon buds and the dendroid is soft connection, right? And when I say soft connection, that means that the connection is not 100% sometimes, or in between 0 and 1. 0 and 1 here would refer to the hard connection and no connection, right? Means there is perfect connection and then there is no connection. In between that can have any degree of connection, and the degree of connection, the transmission of the signal, will depend on the density of the neurotransmitters, right? So that is why the concept of the weight comes into picture. So you can see the weights, all the inputs are along with the weights, W1, W2, W3, and so on, as per as per the number of inputs that is connected, right, through the axon. So this W's value is normally in between 0 and 1, depending upon the kind of connection, the characteristic of the connection that dendroid and the axon bud has. All right, so we have the natural neuron. This is the natural neuron or biological neuron, and then we have the mathematical model of that neuron. So in mathematical model, we have dendroids. You can see through which these inputs are coming, right? And then we have the inputs that are coming through the dendroids are weighted inputs, right? Weighted means the W's, W1, W2 corresponding to the X1, X2 are there, right? That means the depending upon the connection and the transmission of the voltage signal that is coming from the previous neuron is. And then finally, we have the summation of all the inputs here, all the inputs, all the weighted inputs, and then we have a bias here, right? A suitable bias is there. This is also learned, and all of these is passed through the activation function. That means the fluid here, this is the fluid, right? The fluid present in the cell body. So the activation function signifies that whatever input that is here, right, total input is passed through F. So that is why it's a function of F, right? And finally we get the output. And please note that a natural neuron does not have any continuous type of output. It is the discrete output always. It's an impulse type of output. That means it is discrete. And the frequency of this output can be at the most 100 hertz, right? So in 1 second, it can generate only up to 100 impulses at the max. It can be even lesser, right? So this was the time, this was the first time, a learning strategy was provided, a platform was provided by giving a model, a neuron model, the AI, the artificial neuron model, right? And this was the major landmark. And before this, there was a landmark when Turing machine came in 1937, 38. And that time, the engineering landmark we can also include. And before that, there was no mention of any kind of such learning or responding or responsive mechanism through which we would understand that this is this has any learning strategy. But when we talk of AI in philosophical sense keep on existing for many years, but in engineering sense, AI and the learning mechanism was not there. So first landmark that we could see in literature is the Turing machine, the universal computing machine, that is also the same. And then the development, the proposition of the artificial neuron model. And as we know that we have in our brain for carrying out certain processes, certain functions, we take the help of tens of thousands of neurons together. Here also, when we are using the training the model for carrying out for modeling up any process, right? We also have the bunch of neurons together interconnected. Okay, so all these the setup, that is interconnected setup, we refer to as the artificial neural network. So the name has come accordingly. When we have a neurons, multiple neurons interconnected, we have a neural network, artificial neural network. So there are so many types of topologies. The one we could see here is the very simple topology, that is the feed-forward neural network. Here we see a feed-forward neural network, right? And in feed-forward neural network, we have, you see, the first neural layer, right? The first layer, you see, this will form the first layer. This is called zeroth layer, the input layer. And the last layer, right, that is the final layer, is called the output layer. Okay, and here we have these two layers fixed, and then any number of layers in between are termed as hidden layers. So here in this example, we have how many hidden layers? 3 hidden layers, right? So we have a feed forward topology of artificial neural network where we have 3 hidden layers. Right? There is no limit of number of hidden layers. It depends as to how many number of hidden layers you need, and accordingly you include in the neural network. And of course, it is needless to say that the number of hidden layers may be required or unavoidable depending upon the nature of the processes based on its degree of the complexity, non-linearity, or maybe sometimes, if it is highly non-linear or maybe uncertain system, right? So more and more hidden layers may be needed to model any process accurately. All right, so sometimes we are needed this the number of hidden layers, and we cannot avoid it. And I would like to mention here that very basic kind of training mechanism, training algorithm is available, which is called a back propagation algorithm for neural network, and which is very helpful in getting the neural network trained, right? A very basic, very popular, right? It was proposed in 1965 around. I mean, in 60s only it was proposed, but it took around 4 decades to get matured finally. And nowadays, you see, before the deep learning, the back propagation has become very, very popular. Almost any of the or all of the applications of neural network required this back propagation algorithm. All right, but this back propagation algorithm has certain deficiencies, certain issues. What is this issue? Is basically, it has some inaccuracies. Like when we develop a mathematical model of using neural network, sometimes you get a very good accuracy, and the same model for the same problem may not be giving you the that level of accuracy, right? So it is because of the random initialization of the parameters of the network, like weights, biases, and there are other parameters if we are interested in taking like activation function parameters as well. So this is the major problem here using backpropagation algorithm, because backpropagation, once again, I would like to mention that it actually initialize the parameters that it is learning randomly. So we do not know what is the weights that is going to be taken, and all the time when you using the network is taking parameters randomly. So that is the major issue, and because of this, the global optima cannot be ascertained. So global optima is not there, right? It works in the local optima, and that is a major challenge using backpropagation algorithm. And another thing is when we have the process which requires uh, number of layers, more number of layers, right? Like 2, 3, more than 2, 3 hidden layers, then the gradient vanishing issue starts coming. What is gradient vanishing issue is basically, so in backpropagation algorithm, we take the gradient of the error, and that is helping us in optimizing the parameters of the network. So this basically, when we have the more number of hidden layers, then only first few layers from outside output backward works well, and when we go a little deeper, we find that it is not very effective. So that is why the backpropagation algorithm for more number of hidden layers, it is not very efficient. It is not working for the initial layers, right? So that is if that is the case, then what happens? Some inaccuracies remains, right? Means the learning is not happening the way it should have been. Right? So now to deal with this problem, we have strategies called hidden deep learning strategy, and I'll just introduce the deep learning deep learning strategy in coming slides. So this random initialization, as well as the number of hidden layer, basically play main role, and you see it is because of that you have local optima, right? And then the number of hidden layers are actually not training the initial layers properly. So you see, we look for the other alternatives. One of the alternatives that we kept on looking at was deep learning strategy. So let me tell you, deep learning is also not deep learning is not a new strategy. Deep learning is a very old strategy, but it was it was also not mature till the time when Hinton, Bengio, and Lacan came with the successful solution of the deep learning, right? The training solution in 2006. Okay. And then afterwards, you see, when this strategy came, the learning strategy came, this kind of problem was avoided. So let me tell you that this is the indicative example. So let me tell you, if we have multiple layers, right, in the network. So first few layers, are termed as low-level features, right? And we can understand that way. So more and more hidden layers will basically help us in understanding the refined features, right? So that is why, if we have more hidden layers for complex problems, we have better expression, we have the better understanding of the data or the non-linearities. Okay, so that is why we need we cannot avoid the hidden layers. Rather, we need hidden layers, and we need the proper solution to train these such networks. So deep learning basically is a strategy, right? A set of algorithms that is developed to achieve deeper intuitions and intricate structures in the data. Okay, so deep learning framework comprises of multiple layers of nonlinear processing nodes. It can be a neuron. So that is what I would like to mention here at this point, that you see the network node can be any nonlinear node, not necessarily the neurons. And deep learning strategy can be applied to such networks, right? But here, the example, while successfully, defining or successfully giving the solution of the deep learning, the neural network was used by Hint and Benjio and Lacan in 2006. And deep learning strategy was, the term was coined in 1965 by Ivanko and Lapa. So all these things indicate that, like backpropagation algorithm, the deep learning algorithm was also, the efforts were on to get it matured. So each layer in DL, the deep learning framework, represent higher hierarchical level of abstractions that I just mentioned through the images. Like the first few layers are the initial layers are basically the crude features and then refined features and all. And finally, these features are helping the classifiers to correctly understand or they classify the labels. So deep learning algorithms find very complex, meaningful patterns in and structure in a large scale of unlabeled data. All right. So deep learning algorithms have revolutionized representation learning in unsupervised or supervised, semi-supervised manner, thereby improving state of the art in various fields of computational intelligence or AI, such as object recognition mainly, and detection, and NLP, speech recognition, etc., like in big data analysis, etc. And deep learning, when it is applied to neural network, it gave rise to the deep neural networks, deep belief networks, convolutional neural network that we most of us are using, taking the help in of CNN in computer vision, and then recurrent neural network, that is very popularly known as RNN, and GMD is that group method of data handling, and like that. So all these networks are there that are using the neural network, right? The artificial neurons, a set of a group of artificial neurons, all right? And when these nodes, nonlinear nodes, are basically replaced by, I mean, these nonlinear nodes are some other nodes. Like we have seen a network in deep neural network, we have neurons, and if these neurons are replaced by some other artificial non-linear nodes, right? So accordingly, the name can be changed, and the power of that non-linear nodes can also be accumulated and harnessed, and then suitable deep learning algorithms can be used to learn this, and then this further can be used for various applications like fuzzy networks. For deep fuzzy networks, I will be discussing in the coming slides, and where we'll see, like I just mentioned, deep neural network. where the neuron was there as nonlinear nodes. So when we discuss deep fuzzy networks, we have a fuzzy model instead of a neuron as the nonlinear nodes. So we'll be going through that in coming slides. So this is how the deep learning strategy works. Like we have a network where we have the input layer, output layer, and then we have all these hidden layers. These are the hidden layers. These are the hidden layers, right? Hidden layers. And these nodes are some nonlinear nodes, not necessarily the neural, the neurons or the neural network. Okay, so that must be understood carefully. Now, let me take you to the time when deep learning strategy was, deep learning name was coined. So, the first deep learning model as well as the deep learning term was coined by Ivanko and Lapa in 1965, right? And as I mentioned that, you see, the backpropagation algorithm was also uh, proposed during that time, around that time in 60s, but it was not well matured. So to train this network, the help of polynomial activation functions and statistical learning methods were used. And you can see here the network. You can see here the network which was taken by Ivanko and Lapa when the deep learning was suggested. Deep learning word was coined, right? The model was proposed. So this is a very simple, and we have the input layer, you see, and then we have the output layer, and in between this we have three hidden, right? So this was the basic model, the model that was initially taken, right? And then finally, but that time it was not very conclusive and nothing came out of it. The network was not trained the way it was, targeted, right? So finally, as mentioned by, as I mentioned by Hinton, Bengio, and Lacoon in 2006, the learning strategy through deep learning came into literatures, and since the time, the deep learning has become very popular with respect to the neural network. So deep neural network was very popular, has become very popular. All right. So this is how it progressed, and as mentioned, the deep learning is independent of any network. So the kind of network can be any network, and the deep learning is a strategy which can be applied to that network, and accordingly, we can get the we can accomplish the results. So as I mentioned, when we apply the deep learning strategy to neural network, we get a deep neural network, right? And as I also mentioned in the beginning, in few slides before that, initial layers, here represents the features, and then successive layers represents more features, more refined features. And deep learning are the network which requires more and more number of hidden layers, are basically helping us to model highly non-linear kind of process. For example, if we have the image recognition, right, the face recognition, like that. So this is a very highly non-linear process. Okay. So this kind of application definitely require very high grade of nonlinear relationship modeling, relationship defining, and because of that we need more and more number of it, and that's why the deep learning for such kind of problems help us very much. And this is what I mentioned in 2006. Hint and Benjio and LaCun came up with the strategy, and they published 3 applications on the same strategies, right? And since then the deep learning has become very popular. So let me tell you a very basic learning mechanism. So let us assume that we have a network, we have a neural network which we are trying to model, and this network has, let's say, many number of hidden layers, like n number of hidden layers. So, and please note that through deep learning strategy, there is no limit of the number of hidden layers, right? So we can have any number of hidden layers, and the network can be very accurately managed or the modeled. So we have to first break any network which we are trying to model through the deep learning strategy. We have to break it into parts, means into layers, and each and every layer is basically modeled separately and then cascaded, right? So let us assume that we have this kind of network. So this is the first, this is the hidden layer, and then we have the first, this is the input layer, and then this is the first hidden layer. So first hidden layer is first taken and modeled it, right? We make the autoencoder. I'll just go through this here, this slide. Let me go to this slide. Yes. So we develop the autoencoder, right? So we call this as here. So we have the input layer, and then we have the hidden layer. So let us take the first hidden layer. This is the first hidden layer, okay? And before this, the input layer we have here. And what we do, we basically we develop an autoencoder, right? So we give the target of the same input, right, to generate the same input by the number of the minimum possible number of hidden layers. Or if the let's say hidden layer already is defined, then it's fine. But otherwise, let's say if we have to optimize even the number of nodes also, then we take the best minimum possible. So let us assume that we already have the number of hidden layer nodes. So we start with that nodes, and you see, we give the target to estimate the same input, right? Or the we give the target of modeling the same or generate the same output, right? So you see here x1 cap means we are generating here the same amount of output, right? The amount of output that we are giving. So by simply, using the backpropagation algorithm or any other learning optimization algorithm, we can optimize the parameters here, the weight parameters and the bias parameters, right? And this is what is called the encoder, right? And then finally, from with this, we should be able to generate this. So here also we get the output, the weights. All these are the weights. All these are optimized. So this is called decoding, and this is called, this is called encoding, and this is called decoding, right? So here we can decode whatever is output here, right? From here we can decode the input, right? So if this is done, right, then our job is done at this point. So this means that we have the parameters at least coarsely found, right? So input vectors are there, and then the first hidden layer is there, and this first hidden layer is modeled, right? The first hidden layer parameters are found by suitably, developing the autoencoder. Now, the way we have done here, we do it for all the successive hidden layers. And in case if we are feeling that the data has some noise, so we can denoise also through developing the autoencoders, denoising autoencoders. So here what we do, we have the input vector, right? And we give some corruption, some mixing of the noise, and then we found the same, we try to decode the same input, right? So if that capability is achieved, right, we call this as the denoising autoencoder. So a very good example is here. You see that the noised data is here, and with the help of this kind of autoencoder, denoising autoencoder, this can be modeled very well. So the way we have developed the autoencoders for the first hidden layer, all the successive hidden layers are modeled, or the autoencoders are developed, and you see all the weights that are found are used for further training. And this kind of development, this process is referred to as the course training, right? So this is the course training, and then finally all these are stacked successively. All these the layers that are modeled, that are the parameters that are trained, we use for this network, and then we use the classifier, some suitable classifier, preferably softmax classifier. This is a probability based classifier. So we use it, and now we have a supervised kind of strategy, right, for fine tuning. So earlier one was unsupervised, because we were using only the input that was there, input to the previous input to the hidden layer, and the same was used to found the parameters coarsely. Here we are fine tuning, right, through either the back propagation or some suitable training. So this is basically a two-stage learning. First stage is coarse learning. Second stage is the fine tuning, right? And you see here, this whole strategy is supervised because we have a softmax classifier, or any other classifier can be used. Whatever you wish, you can use. And this will be able to help us in giving the global optima. And this is how the neural network with more number of hidden layers can be trained, and it can give us a global optima, right? So this is how, the deep learning strategy we can use for training the neural network. So I think in the next discussion, we'll discuss as to how we replace the neuron as the non-linear node by the model, suitable fuzzy model, and we see what are the advantages, the benefits that we can gain using the same deep learning strategy, right? And then we'll have the question answer session. So I think this 7:55. We'll be meeting what time? I think 10 minutes after or
Yes,
whatever time that you give.
yes, yes. We will now have a 10-minute break and resume at 8:05.
8:05. All right. So we'll meet at 8:05. Thank you very much. All right, so welcome back. Am I audible now?
Yes, sir.
Sir.
All right, so can I start now or
Yes,
should
sir.
we
Yes,
wait
sir.
for?
Yes, sir.
Okay.
Start.
We can start.
Great. All right. So, yeah, in the discussion that we have so far, we saw as to how a neural network with more number of hidden layers, more than 2-3 number of hidden layers can be trained using the deep learning mechanism, right? And deep learning mechanism was proposed for any non-linear for any network which uh, has non-linear nodes. So then, it was realized that fuzzy network or fuzzy model is powerful in certain sense. Like we use fuzzy model when we have data or the process with special kind of uncertainties. For example, the imprecision, vagueness, and ambiguity present in the process or data. So no other mechanism, no other strategy is helpful the way or to the extent the fuzzy based strategies are helping in treating such uncertainty. So then, keeping that in mind, it was proposed that why not we replace the model of the non-linear node by a fuzzy model, by a suitable fuzzy model, which of course is also a non-linear node. So before we moved ahead, or before it was in general sense it was proposed, some test needed to be carried out whether it really does the same or not, right? So we know that a fuzzy inference system, right, a FIS in short, right, is a fuzzy model, right? FIS. So it's a fuzzy model. This involves a set of fuzzy rules and all. So it gets developed based on the data that we use for training the model, the fuzzy model, right? So input data and then the output data. And this forms a single non-linear node, right? And this node could be either based on Mamdani type fuzzy model or the TSK5 type fuzzy model or Tsukamoto type fuzzy model, like that. So here, in the beginning, when we are moving ahead, we proposed, to test whether it really does the job that we are testing or not. So you see, we took some data and we used ANN, right? A simple ANN. And we develop a model, right? Means we understand the behavior of the data. And that means what is basically we identified the parameters, we learned the model, and then we tested the model that it is performing. Its test outputs are matching with the uh, you know proper accuracy or acceptable accuracy. So the same data was used when we took a fuzzy inference system, a fuzzy model, and we found the same, almost same, right, up to that level of the accuracy. And then what we did, we added some inaccuracies, some uncertainties rather, right? And these uncertainties, the kind of uncertainties we took mixed in the data is the vagueness, the ambiguity, the imprecision, right? Like in some cases we miss the data, right? Like imprecision, we created imprecision, and then what we found here is that it is deviating. Its performance is far below than what we were getting before, because the data remains the same. Only the difference is, the only difference here is the uncertainties that we have added here. Right? So what is the change that we observe here is the 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 uh, the performance, the accuracy. Right? It is not able to, the same model is not able to manage the level of accuracy that we have got. And we basically trained the model with this kind of data now, the input plus the mixed with the uncertain data, right? The data little bit modified. Now the same data here, same data, you see, when it was used as the input to a FIS, to a fuzzy model, right? And this fuzzy model was the TS fuzzy model, right? TS fuzzy model. And this fuzzy model was performing much superior to the ANN, right? So it is very clear that fuzzy model is performing in much better for the kind of data that I just mentioned. With any inaccuracies, when uncertainty is special kind, right? So it is now clear that the FIS, the fuzzy model is, with such kind of data, is performing better than what we have in ANN, right? So that means what? That means this kind of uncertainty, the better tool is a fuzzy model. So when we know, or when we have verified that a fuzzy model is working better in this environment, so why not we form a network and which for very complex applications or highly uncertain or highly non-linear processes, use deep learning strategy to train such networks in order to get better performance. So this is what is the aim, and we moved forward, and let us see what we have achieved. So you see the testing error in case of fuzzy, and in case of here the ANN and then FIS. Similarly, the training error, and then the in both the cases, ANN and FIS. So you see the order in which you are getting the accuracy, right? So it is very clear that we are getting less error here, right, compared to the ANN. All right. So when this was verified, then now the path is very clear. It is quite convincing that let us move ahead and apply the deep learning strategy to the network, more complex network, or more or the network having more number of hidden layers, because the deep learning strategy doesn't limit the number of hidden layers. All right. So on the same lines, we move forward the way the deep neural network here we have, right? So similarly, you see, some intermediate processes were done for the the testing of the performance for the same data we used, and we tried to check, and we found the same observation. right? The observation remains the same. Now, so what actually we are gaining and why we are, what is the basis on which we are moving ahead? So first is the kind of uncertainties, the data uncertainties that we are able to deal, which otherwise is not possible. So we call this as, since this is the network based on the fuzzy models, right? The nodes are nonlinear nodes, and these nonlinear nodes are nothing but a fuzzy model, suitable fuzzy model. So we call this as the deep fuzzy network. And this deep fuzzy network can process the uncertainties due to vagueness, ambiguity, imprecision, etc. in in the input, and the actual output is close to the desired output. That is what we are going to get, and that's the motivation, right? And what is the next motivation is, you see here, the next motivation is, the motivation number 2 is, you see, interpretability, right? So let's say we have a network, deep neural network, which is ready for some for some process, and which has been prepared. And in case if we are trying to understand, interpret what is happening even in between, we are not able to get anything out of that, because if we look at each and every node, we'll be simply finding the the matrices and the mathematical expressions only. We are not getting anything out of that other than that. So we see we are going to get this kind of thing, right? And we are not going to infer anything. So we are getting just the weights and biases, etc. And the understanding through that is very difficult. But if we have a DFN, since each and every node is a fuzzy model, and each and every fuzzy model has a set of fuzzy rules, which is nothing but in the expression, the language, the linguistic terms are there in this form, right? For example, if the rule number 1 is, if this particular expression x1 is falling under this range and x2 is in this range, fuzzy range, etc., then the output is defined by this. So something of this sort is available for each and every node. So some interpretability is there. So whatever is happening during the process, the some understanding can be made, and not only that, even some experts' opinion, some experts' experience can also be added anytime in addition to what we have achieved from the data. That means many times what happens, especially in industrial scenario, many times some operators, they don't have any mathematical equation, but they know that if you do this, this is going to happen. Or they have some relation which in mathematics they cannot define, but they can define in rules. So these rules straight away can be added to such information that is available through the model development process, and the benefit of that experience can be accounted. All right. So this way we have 3 main motivations, and with these motivations we moved ahead, and you see when we applied it, and we also know at this point that we can approximate any nonlinear function using the suitable fuzzy model. So there's just the examples, right? So for example, here you have this function or this function. So any function can be approximated. So any nonlinear function can be approximated using the fuzzy model, suitable fuzzy model. So then, of course, when you use a set of fuzzy models, So the even high level nonlinear models or high level complexity can be handled very easily, right? And apart from all these, the uncertainties also. So here we have a win-win situation, right? But at what cost? Cost is the computational efforts, because here we have more number of parameters to estimate than we have in neural network or a deep neural network. But there are situations where is the where we have the accuracy as the need, the requirement, like in diagnostics, the health diagnostics and all, we can afford to have the computational efforts, and this kind of model can be very, very helpful. So here you see an example where we have a deep, a simple network where we have three fuzzy models as nonlinear nodes, and we can use to model some data, and we see the results, and we see the quantum of error, the test error, you see, with the same number of nodes here, same number of nodes, same topology, right? But when we use TS fuzzy model, we get, you see, this kind of profile of the error. See here. And when we use ANN, of course, the error is this. Error profile is this. Okay. So, and then you see the number of the variation of the number of hidden nodes. Okay. So, based on the number of nodes, so when we have one node, the value is this. You see here, this, and then for ANN, you have this as the error. Okay. Similarly, when you have two neuron in the hidden lobe, you can see the error, the difference, right? So like that, you see, fuzzy model is performing much better, but it has certain cost. It's not free. It has the computational cost. Okay. And that's fine when the situation demands that we should have better accuracy, we should go for it. So likewise, we have certain examples where we can see and compare. Now, the next step is to develop the general architecture, right? So the general architecture is same as what we have seen in ANN, right? When it comes to the deep learning mechanism used in ANN, that means the DNN. Okay. The only difference here, for representation purpose, instead of circular node, we have the square node, just to make the difference that this is a fuzzy network. This is a deep fuzzy network, right? And we see that the parameters that we are supposed to deal with or the optimize is with the fuzzy node is, if we this is for the single node, single fuzzy model, is we have input fuzzy membership function parameters we have to optimize. We have to find and or identify, and then we have the fuzzy rule base also we need to find, right? We need to find the rate, and all these are found from the data itself, right? And when we have the fuzzy rule base, we have the fuzzy rule premise parameters, we have fuzzy rule consequent parameters. All of these are found from the data, right? And then when we have all these there for respective fuzzy nodes, then the same process is adapted. We need to find the autoencoders for first layer, and then consecutive second layer, and then third layer, and so on. And then we basically stack them together to finally fine tune with the suitable classifier, right? So we have the suitable classifier here, right? And finally, we take the help of it. So here also, the learning of the DFN is in two stages. First stage is the uh, the post learning. Second stage is the fine tuning. This is supervised. That means the autoencoder is developed, means the same input is used to estimate the output, right? Same input is kept for the output estimation, and in that process, whatever is the best parameter that we get, the weight parameters, we use it in the course structure, course training structure, and then when all of these are done for all the hidden layers, then finally we have a network which is ready to get fine-tuned through the supervised mechanism, supervised learning, and that is using the output levels where a classifier is there, and this classifier basically helps us in fine tuning. And with this, the whole model development is complete. Okay, and this way the training is completed, and no matter how many hidden layers that we have, we start with the back propagation in course training and the back propagation in fine tuning, and this all gets done very easily. And as I mentioned that we have the efforts that are needed to get trained on these these hidden layers is much more than what we have in the artificial neural network through the deep learning strategy, right? So here we have a simple comparison where with the data, iris data, when we have two hidden node, right? Very simple network, a single node, single hidden layer node, right? When we have DFN, you see the order of the error, right? Here, the accuracy, and here we have the accuracy. This is accuracy. So more is better, right? So DFN has better accuracy, whereas the SAE, that means we have the autoencoder, which is less accuracy, right? So that way we have, we can compare the accuracies, and we find that DFN performs much better than the DNN, right? With the same number of nodes. Okay, so for more details, if you are interested, you can follow this paper, and you will be able to get some more information if you are interested, right? And after this, I will be going through the application. I will just discuss the application. Am I audible? Am I audible?
Yes, sir. Yes, sir.
Okay, okay, great. So you see, when this model was applied to the fault diagnosis system, right? So we applied this, and we found it's it's very well performing, very good, giving very good accuracy for the fault diagnostics system, fault recognition system. And the reason is that the input and output data, right, in fault diagnosis is very complex, it has a very high non-linear relation, right? And you see, in fault recognition, we have these steps, that data acquisition, then pre-processing, and then we have feature extraction, feature selection, and classification. So deep learning can very well be used for feature extraction and feature selection. So if we use deep learning, it gives us the automatic, feature extraction, right? So you just feed the inputs, and outputs, and accordingly you can learn the features, the best features. Okay, so that's what is the benefit that we can get in learning the features. And then finally, you can use any classifier when we have suitable features values, and we can manage to get better accuracy in the recognition. So fault diagnosis framework, we have the same line where we develop the autoencoders and then we stack them together, and we finally use the the classifier and get the model trained, and then we verify also with the same unused data. So some of the experiments that were carried out in the lab, our lab, by the students are, we have some data, and where we have we call this as the input data, and then we develop the DNN as well as DFN, and then finally, by using the classifier, and these features are extracted and selected automatically through the deep learning mechanism. So that means the deep neural network as well as deep fuzzy network. And the other method is here. And the conventional method is here, where it is manually done. The features are extracted manually, and even the selection also done manually. So this is not a very good move, where it takes a lot of time, as well as it doesn't give us the accuracy as good as we have for the case where we use DNN or DFN, right? So this is how the use of DNN and DFN we call as high level features, right? It's a better features that we are able to get through the intermediate layers, that means the hidden layers, right? And this is automatically done, right? So we perform this learning for the air compressor and drill bit data sets, and this was very encouraging. And here are some of the the performance of the models that we have for the comparison. So you see, in all the cases where WPT is the man-made feature, right? Means the handcrafted features. So here, and FFT also, the fast Fourier transform, and then the WPT is the wavelet packet transfers, the manually computed this thing. And here, the deep learning based mechanism, when we use FFT, right, we have the better performance, right? So these were the initial studies that were carried out, right? So, but if someone wants, someone can avoid FFT also. We can use directly, and we can learn the intermediate features to manage better. As I mentioned that here the computational efforts are more than the DNN in case of DFN. And when we compare even the DFN and DNN with the simple models that we have, that are handcrafted features like WPT and FFT, of course, the performance is not as good as the deep learning mechanism, but yes, the computational efforts are much less than what we have in case of deep learning based models, right? So DFN basically has the capability to handle more complexity and abstraction in data with smaller architecture compared with DNN, and it is because of the parameters that we are handling in case of DFN. right? And the error is better. The accuracy is better. And working of trained model is understandable of human beings, and underlying working of working can easily be comprehended by the human beings, as I mentioned. And DFN has the asset of dealing with uncertainty of various kinds, such as vagueness, ambiguity, and imprecision, etc. And then DFN is robust and in presence of noisy data. And then prior human supervisor knowledge, etc., can be easily incorporated into the architecture of DFN. Then we have closely matches with human cognitive thinking, right? So that way, you see, we have, we have uh, come up to the level where we can see that fuzzy-based deep learning strategy is working better in cases where we have highly complex, highly nonlinear, and the data with uncertainties, special kind of uncertainties like the vagueness, ambiguity, and imprecision, etc. present. All right. So this way, you see, uh, uh, we claim, but uh, you know, you see, the efforts needed are also prominent, as I mentioned. Okay, that means it is highly computationally extensive and expensive, right? So this is how it goes. And here there are references in case you wish to move ahead. You can refer, and those of you who are interested in working in this area can manage to get more information. And at least going through this will give you, uh, uh, working knowledge. All right. So thank you very much. If you have any question now, we can start discussing.
Sir, can we take a break for a few minutes?
Okay. What time should I
Uh,
rejoin?
we will begin the Q&A session at 8:50.
8:50. Okay. Okay.
Participants having any questions, they can type it in the chat box or they can raise a hand. We will unmute them. Thank you.
Okay. Sure. So we'll meet at 8:50 then.
Yes, sir.
Okay. Thank you. All right, so welcome back to the question and answer session now. Am I audible now?
Yes.
All right, okay. Let us go ahead.
Participants having question, please ask. They can type it in the chat box or they can raise hands. We will unmute them.
Any questions, please?
Any queries from participant side?
Looks like there is no question from any participants. Please come forward for any questions, any doubts that you have during my presentation.
So there is a question in chat.
Okay. Let me just check. Okay, there is a question from Hari Om Pawar. Does deep learning give solution to send information quick to receiver? For example, there is a device which detects gas and the information will go to the owner. Right. So the question, you know, basically, it depends. If you have the question which involves any process to be modeled, right? And here, uh, the deep learning gives solution to send information quick to receiver. I think it's not very clear to me what is the exact question, but let me tell you, if you have any process that needed to be modeled, right, through black box model, so in that case it helps. All right. Otherwise, it's not very clear to me the question. In fact, the question, what exactly you are interested in asking. Okay, so wherever you are interested in developing or understanding the process, basically deep learning helps, and for that you need to have the experience of the data that is used for training that model and accordingly validated the model for further use. So am I okay to I mean, had I answered the question that you have raised, or if you are there online, you can discuss with me your query. Probably that will
Unmute
help me
Shashwat.
understanding.
Shashwat,
Yes, ma'am. Yes, ma'am.
Shashwat, allow the participant to unmute and then ask the questions so that it's better.
Yes, ma'am.
In between, anybody else has any query? So we have some participants from
Hello.
this. Hello.
Okay.
This is
Yeah.
Arjun Paul, ma'am. Am
हाँ,
I audible?
Yes,
yes.
you are audible. Please go ahead.
Sir, I have heard your presentation and I have just one query. If I have designed one gas sensor which can detect the amount of
Oh,
gases.
wait. You are developing a gas sensor, right? For
Yes,
example,
for example,
okay,
yeah.
okay,
And
okay.
now what
So
I'm think,
let me just ask the question.
yeah.
So is this gas sensor, modeled gas sensor?
Sir,
Like,
still we
is
have
it
just designed a sensor which can detect the gas in terms of ppm.
okay?
If
Okay.
there is higher ppm, it can detect and it can inform the yes, there is a gas present in environment. If we are talking about
Okay.
specifically kind of reducing gases. But my
Correct.
question
Correct.
is that on the base of this presentation, can we design
Mhm.
any model, any model which can inform to the particular person? Suppose we are designing a sensor for the LPG detection for the home purpose,
Let
home
me
apply.
let me tell you. Let me just interrupt here.
Yes,
See,
sir.
while designing the sensor itself, you can get a better model, better sensor, right?
Yeah, yeah,
So
yeah.
here you may have the physical sensor, but you can have an algorithm based on deep neural network or deep fuzzy network, where you get a better sensor, better instrument, right? Based on that sensor. So at this stage itself, you can get the benefit of DFN or DNN. Okay.
Oh,
And then the next stage that you are mentioning is the informing, right? So I am not sure what your question is, for information, providing the information to, or maybe the transmitting the information, that I'm not sure. So could you please just let me know what is your question forward?
yes, sir. Yes, sir. Sir, my question is for the layman people, like who is not too much literate, but at least
Okay.
in if we see the government scheme, initially that Ujjwala Yojana was started from the PM Modi, right?
Mm-hmm,
So
mm-hmm.
what they are doing, the people who are far away from the this innovative technology and all, they are providing them the gas cylinder and all. But what I'm
Right.
thinking that they, even though most of the people, they are even not aware how to use it. And sometimes there is some tragedy happening, they are leaving the leak and there will be a leak in home. And as they are using,
Okay.
it is just a blast. But
Mm-hmm,
what I'm thinking, if we are designing some kind of sensor, it will be
mm-hmm.
very cheaper. But how we can model a system which can just give the information to the particular person? Suppose right now, if we see everybody are using the mobile phone, everybody.
Okay.
So if we can design some kind of model
Okay.
which
So
can,
yeah, I probably I got your point.
yeah,
So
yeah,
yes, deep learning strategy based sensor, right? Some artificial sensor can be developed and can be embedded in the at the I mean the instrument which is placed at the end user. Okay, and that could be probably the mobile based system or Android based system. and that in case of any hazardous activity, or maybe it is probable to be hazardous or something like that,
Yes, sir.
right? It can fetch the information to the concerned people so that the next action can be taken. So that can be done. Yes.
Okay, okay. And sir, one more question I have. Sir,
Yes,
do you
please.
think like if we design this kind of thing, it will be cheaper?
What is cheaper? What?
Like in terms of the cost, because the most of the people are looking forward the cost. If the cost is
See,
higher, then they do not
sometimes, no,
prefer.
no, no. The cost, see, the cost factor depends on many things, right? If it is
Yes, sir.
produced in bulk,
Mm-hmm.
then definitely it may be very cheap and affordable to people, right? The common people. But if it is developed and it is at the initial stage where very few sensors or such instruments are developed, then of course at that level that will be a little higher.
Okay, sir. Okay. Thank you so much, sir.
But yes, final cost will depend on many other factors, right? As to what you are doing, what level of diagnostics, like developing the artificial sensor and all you are developing.
Okay, sir. Okay.
All right,
Okay. Thank you, sir.
no problem. Any other question, please?
Sir, as you know, this FDP is a combined FDP for the computer science and the chemical engineering faculty members. So,
Okay.
can you please suggest some, one or two applications for the specifically for the chemical engineering faculty and the research scholars, so that how they
Yeah,
can
I think
like
this was a very good example that we just
yes,
discussed.
yes,
That
yes.
we
One,
see
some more,
sometimes
sir.
we
One, two, one
right,
or
sometimes we come across developing some sensors where we have the input data and the output data, and we do not know the physics of the sensor, right? That means the chemical reactions and all, right? And at least these can be modeled through the data, and accordingly, the sensor performance can be enhanced, and sensor, at least the process can be modeled. So these kind of things can be tried. And similar to this, there are many other applications in chemistry, right? The chemical engineering and all, similar to this, can be modeled whose chemical reactions are not known or difficult to be identified.
thank you. Anybody else has any questions? Sir, we discussed that the fuzzy performs better than the normal ANN or DNN. So,
Right.
what what's the reason why it performs
Right.
better?
So, yeah, madam. So, the reason here is very simple. When we deal with any fuzzy model compared to the neuron as the non-linear element, non-linear node, we see that here in fuzzy model we have parameters, multiple parameters, at least parameters more, the number is more than what we have in non-linear neuron, right? And these parameters are getting adjusted suitably to get the function approximation, nonlinear function approximation at various stages that are there to be identified, to be modeled. So that is what is the main reason. And in this process we have to exert towards or in other words we say the computational efforts are needed, right? So that is what is the cost and the benefit involved.
means that when before using it, we need to check the balance between the cost and the performance
Right,
as
madam.
per
So,
the application.
right, as per the application. So many a times accuracy is very important. For example, where let's say we are, diagnosing, we are using the DFN for health applications, right? And we are modeling some process where ECG, EEG are some such parameters are involved. We would prefer to go for it because we are interested in better diagnostics, no matter how much it is expensive, right? Because here the question of life and death is there, right? So for such applications, we don't bother about the computational efforts. Yeah. Okay, madam.
Anybody else has any question? Participant? The participants are not having any questions, then we can just thank sir.
Yeah, you can even later. I'm just requesting participants in case you have any query or anything related to what we have discussed today. You can email me, and I will try my best to address your queries.
Thank you, sir. Thanks a lot for that. Now the
No problem.
formal thanksgiving will be by Rajeshwar.
Thank you, madam.
Okay, ma'am. Uh, I would like to extend my gratitude to Dr. Nichal Verma for sparing his valuable time today. Sir, your presentation was very insightful and provide with a lot of valuable information regarding deep learning and deep fuzzy network. I truly feel that this knowledge will help us a lot in our respective field. I thank to program conveyor Dr. Kailas Singh and coordinators Dr. Shushant Upadhyay and Dr. Meenakshi Tripathi for well organizing first part of FDP on online mode at MNIT Jaipur. Also, I thank all the participants for joining this session. As we know that this faculty training program has been divided into two parts, that is online week FDP and offline week FDP. Now, today, online week FDP has been successfully completed. For offline FDP week, all of you have to come physically to MNIT Jaipur to attend the sessions as per the schedule in between 16 to 20 January 2023. The inaugural ceremony in the offline mode will be held on 16 January at 9:30 in the morning at Nitish Sabhagar, Prabha Bhavan, MNIT Jaipur. Invitation of the ceremony is already sent you through email. I request all the participants to make sure that you join the inaugural ceremony on time. Also, please note that attendance is compulsory for all the participants for all the sessions for both online and offline FDP week to get the participant certificate. Now, I request program coordinators, will you guide something regarding offline FDP week, or will I announce that the session is over?
Okay, thank you, Mr. Rajeshwar, and thanks a lot, Professor Nishal sir, for explaining the concept of deep learning in a very lucrative manner. Thanks a lot for a very wide explanation, and I think the participant has
Welcome. Thank you.
benefited definitely from this presentation of your great experience and knowledge. And now there is an announcement to the participant that the offline mode of this FDP, Atal FDP, will be held rather than Niti Sabhagar. It will be held in the Malviya Sabhagar in the same premises of Prabha Bhavan. So please note that we will send the separate email ID for the venue, that is a Malviya Sabhagar, and it is very mandatory to attend this course in the offline mode because it is a mandate of AICTE to attend the second part of the FDP in the offline mode. So we will send the separate email, and our student coordinator will also contact to you through your mobile number accordingly, so that you can give the consent. If you want to stay in the guest house, it is a first come first serve basis, then it can be accommodated on the best time. At the same time, we have sent the Google form, but I think many of the participants is from Jaipur only. So it is mandatory to join the offline session of this program to come to MNIT Jaipur at Malviya Sabhagar. Thank you.
Thanks a lot, Professor Nishal.
Thank you very much. Thank you all. Special thanks to all the organizers, especially students and Professor Meenakshi Madam. Thanks to all the participants once again.
Thank you.
Thank you, sir. Thank you. On the behalf
Thank
of
you, sir.
program, I announce that online FDP week is over now. See you at MNIT Jaipur. Thank you so much.